Dear students, in this section we are going to discuss how to calculate kinetic energy of a body in combined rotation and translation. Let us take a rigid body. You can observe here this rigid body is having combined translation and rotation motion. Here the center of mass of the body is translating with the velocity Vc and the body is rotating about its center of mass with the angular velocity omega. Here we can consider this motion as a superposition of the pure translation and pure rotation, like this. Okay. In pure translation, what happens? Each and every particle of the body move with the same velocity as the center of mass. You can observe here particle 1, 2, 3 and any of the particle is moving with the same velocity as center of mass, right? That means the kinetic energy of this object or body can be represented by half capital M multiplied by Vc square, like this. Capital M is the mass of the rigid body. Now consider the case of the pure rotation. In pure rotation, we assume the total body or combined body or rigid body is rotating about center of mass, that is center of mass is not translating and total body, combined body is rotating about the center of mass. Here in this case, each and every particle of the body is rotating with the same angular velocity omega, and in this case we can define kinetic energy of the object as a rotational kinetic energy that is equal to half Ic omega square. Right. Here Ic is the moment of inertia of the object about the axis passing through the center of mass. Right. Now we can write the total kinetic energy. Total kinetic energy is the summation of the translational kinetic energy and rotational kinetic energy. As we have written, translational kinetic energy is half mvc square. So this is the half mvc square and rotational kinetic energy is the half Ic omega square. So this is the total kinetic energy, right? Here the first term, this one, this signifies the translational kinetic energy of the rigid body, which can be understood as the kinetic energy of the center of mass of the body. Okay, and the second term gives the kinetic energy of rotation of the body and it is called the rotational kinetic energy. Okay. Now let us discuss few important points. Point number 1, a body is rotating about fixed axis of rotation. Let us consider one case. Suppose this is a rigid body, okay, and it is having mass small m, and this body is rotating the vertical plane about this point, say point P, with angular velocity omega. This point P is a fix, that means axis is passing through point P perpendicular to the plane, and this is the mass, center of mass C, right? The weight of this body will act through this point and velocity of center of mass say is Vc. This is omega. The distance of P and C is small r. Now we can make the relationship between Vc and omega and r. We can write this Vc equal to omega multiplied by r, right? You can observe here this body is having the combined rotation and translation motion. Why? Because center of mass of the body is not fixed, it is moving. That means it is having the translation motion, and body is rotating about this fixed point. That means its motion is also rotational motion. So this is the case of the combined rotation and translation, and in this case we can write total kinetic energy, that is K total equal to K translational plus K rotational. Okay, so here we can write half m Vc square plus half Ic omega square, right? Let us rearrange this term and write this Vc equal to omega r. So let us write this term first. So this is 1 by 2 Ic omega square plus 1 by 2 m multiplied by omega r whole square. So this is equal to 1 by 2 and in bracket term will be Ic plus m r square multiplied by omega square. Now you can observe this term, that is the IC plus mr square. This is nothing but moment of inertia of the body about an axis passing through P. You can observe here, this is the application of the parallel axis theorem. So here we can write this is equal to half IP multiplied by omega square. So we can write total kinetic energy as half IP omega square. Okay, here IP is nothing but IP is the moment of inertia about fixed axis of rotation. Now come to the second important point. If a body is rotating about a fixed axis and is spinning or rotating about its own axis, then we can write total kinetic energy as K total equal to K orbital plus K spin. K orbital is the kinetic energy due to rotation about fixed axis, and K spin is the kinetic energy of the body spinning about its own axis. So this is the total kinetic energy in case body is rotating about fixed axis and is spinning about its own axis. Okay, so now let us move to some application part. Here we are going to take few selected illustration. Through these coming illustration, we will discuss the concept which we have learned. So come to illustration number 1. Here you can observe this diagram. Question is the uniform rod of mass m. Mass of this is small m. Length is small l. Is kept in the smooth horizontal plane. This is kept on the table, smooth table, and A and B of the rod move with the speed v and 2v respectively. This is 2v and this is v. Find the kinetic energy of the rod. You can observe here, the center of mass of the rod is not fixed. It will translate and the rod will rotate. In which sense? You can observe here, the sense of rotation should be clockwise. So this is the case of the combined rotation and translation. So here we need to calculate the total kinetic energy. Okay, so let us write this problem and make diagram to the next page like this. Okay, C is the center of mass. Let us assume velocity of the center of mass is Vc, right? And this rod is rotating in the clockwise sense as we discussed, because velocity of B point is greater than the velocity of A. So sense of rotation should be clockwise. Let us assume angular velocity is omega. Okay, now we can write velocity of end A, that is end this end. Velocity of end A should be equal to velocity of A with respect to C plus velocity of C. This is a vector relation. Now we can make our direction. Let us assume right direction is the positive x direction and left direction is negative x direction. So here we can observe here the velocity of end A with respect to C should be in the leftward direction, and velocity of C is given in the rightward direction. So let us make the vector diagram. This is the velocity of A with respect to C, and this is the velocity of C, right? Velocity of the center of mass. So net velocity should be the vector summation of these two vectors. Now the distance of this point A from center of mass is L by 2, and the angular velocity we assume as omega. That means this vector will have the magnitude omega multiplied by L by 2, and direction is minus I cap. So we can write here this VA with respect to C equal to minus L by 2 omega I cap, and this direction is obviously this is the positive x direction. So VC vector equal to VC I cap. Now we can substitute this value and this value in this equation. In this way we can get the velocity of end A, but velocity of end A is given as V vector, which is in the negative x direction. So here we can write V I cap minus V I cap equal to this value, right? Like this. Here we can ignore I cap, so we can write minus V equal to VC minus L by 2 multiplied by omega. Let us call this equation as equation number 1. Now let us move to analyze point B. Point B, if we make the vector diagram, right, let us write equation for A. Now we can write vector equation before making the vector diagram. Velocity of B is equal to velocity of B with respect to C plus velocity of C. Okay, this is the vector diagram. You can observe here velocity of B with respect to C will be in the rightward direction. Okay, because sense of rotation is the clockwise. So this point will move in the rightward direction and velocity of C in the rightward direction. So these two vectors will be like this. Now come to analyze this vector. Angular velocity is omega, distance is L by 2 and direction is positive. So this velocity of B with respect to C, we will write L by 2 omega I cap. And Vc is nothing but we don't know the velocity magnitude, we know the velocity direction. So we can write this is Vc I cap. Now we can substitute these two values like this. Okay, and we know this velocity is given as 2v, that's why we have written 2v I cap. Now here we can ignore I cap. So velocity of end B will be equal to 2v equal to Vc plus L by 2 multiplied by omega. Okay, now let us write these two equations. First equation is minus V equal to Vc minus L by 2 omega, and second equation is 2V, that is Vc plus L by 2 omega. If we add these two equations, this will get cancelled. That will 2Vc is equal to V. That means Vc is equal to V by 2. And if we substitute the value of Vc, we can get the value of omega. So let us write the value of Vc and omega. Now, omega is 3V divided by L and Vc equal to V divided by 2. Now we got the angular velocity as well as the velocity of the center of mass. Now let us come to calculate the total kinetic energy. We know rotational kinetic energy is equal to half Ic omega square. This is the formula. Ic is the moment of inertia of the rod about the symmetrical axis, that is equal to ml square by 12, and omega we have calculated. This is having 3v divided by omega. So let us substitute this value. Now we can solve here. We will have v square term and L square, and L square here will get cancelled. So after solving, we will get this term 3 by 8 mv square. This is the rotational kinetic energy. Okay, now come to calculate the translational kinetic energy. Translational kinetic energy will be equal to half mvc square. Now let us calculate the translational kinetic energy. Translational kinetic energy of the rod can be written as half mvc square, right? And vc we have calculated. This is equal to v by 2. So this is equal to half m multiplied by v by 2 square. This is equal to, after solving, 1 by 8 m v square, right? Now total kinetic energy is the summation of the rotational plus translational kinetic energy. So let us calculate the total kinetic energy. After adding these two values, we will find the value. This is 1 by 8, this is 3 by 8. So this is 4 by 8 mv square, that is equal to 1 by 2 mv square. This is the total kinetic energy. So this is the total kinetic energy of the rod having the combined rotation and translation. We can calculate the angular velocity of the rod and velocity of the center of mass of the rod by Icr method. Icr means instantaneous center of rotation. So let us learn method number 2. Okay. So let us draw a diagram here. This AB is the rod and C is the center of mass. In the question it is given and A is moving the velocity 2v. So we will draw a arrow of 2v in the rightward direction. End B in the question giving is moving in the leftward direction with velocity v. So we will draw a arrow having half of this length. This is velocity of end B. Now what we will do, we will join the tips of this arrow, these two arrows. So let us draw by this dotted line. You can observe here this dotted line is cutting at this point. This point will be the position of the ICR. O is the position of ICR. Here we can assume the total body, in this case our rod. We will assume the rod is rotating with the angular velocity omega. This omega will be same as the angular velocity about the centroidal axis, because in case of the rigid body we know the angular velocity remains same about any point. So the total body is rotating about the ICR with the angular velocity omega. Okay. Now point C, that is the center of mass. Center of mass will move with the velocity vc in the rightward direction. Okay. This is the distance x we assumed, and this distance should be equal to L by 2 minus x. We have written this point as b dash and this point as a dash. The distance of A from this point should be equal to L by 2 plus x, because this is x, this is L by 2. So this distance should be equal to L by 2 plus x. This distance is the distance of point A from the ICR, and this distance is the distance of point B from the ICR. Now you can observe we have the two similar triangles. This is lower one and this is the top one. Okay. Now we can use the property of the similar triangle, because these are the similar triangle, these angles are same. Okay. Now we can write A dash divided by AO, that should be equal to B dash divided by BO. Okay. We are assuming here total body is rotating about ICR. That means pure rotation about ICR. Now in place of A dash we can write 2V, in place of B dash we can write V, and in place of AO that is equal to L by 2 plus x, and in place of BO we can write L by 2 minus x, right? We can observe here this is the center of rotation, this can be assumed as a radius, and this is the velocity of point A. That means this term 2V divided by L by 2 plus x will represent the angular velocity. Similarly, this term will also represent the angular velocity omega of the rod about ICR. Okay. Now we can solve this equation, this one. We can observe this V and V will get cancelled. Now we can write L 2 multiplied by L by 2 minus x, that should be equal to L by 2 plus x. Okay. Now if we solve this, this should be equal to 2x and this is x, that is 3x equal to L by 2, right? This is L by 2 minus L by 2, that will be L by 2. That means x equal to L by 6. So let us write this value of x. Okay. Now we can write expression for the angular velocity. We can find the angular velocity if we substitute the value of x in any of the equation. So let us write the value of x in this equation. So omega equal to V divided by L by 2 minus x and x equal to L by 6. After solving, we can find omega equal to 3V divided by L. This is the angular velocity. Now linear velocity of the center of mass, this should be equal to omega multiplied by x, and x we have already calculated. So this is Vc equal to 3 by 2 V L V divided by L multiplied by L by 6. This is equal to V by 2. We can observe here the velocity of the center of mass and angular velocity of the rod we have calculated by using this method is same as the velocity we have calculated in the previous method. That means the total kinetic energy will also be the same. So total kinetic energy should be equal to half mv square in this case also, right? One more important point. We know the Icr property, that is the instantaneous center of rotation property. We know the total body can be considered as pure rotation about Icr. That means the kinetic energy of this body, this rod, should be equal to half IO multiplied by omega square, because the axis passing through the instantaneous center of rotation can be considered as a fixed axis, and in case of the fixed axis we can directly write kinetic energy as half IO omega square. So let us write kinetic energy as half IO omega square. IO is the moment of inertia about the Icr. Moment of inertia about C, that is about the centroidal axis, is IC, and distance between the axis passing through C and O is x. So moment of inertia about O should be equal to IC plus mx square. So this term will be like this. Now we can substitute the value of x equal to L by 6. We have calculated the value of x here, x by L by 6, and IC equal to ml square by 12. Right, and omega we have calculated 3v divided by L. After solving, we will get the same value, that is half mv square. Now let us move to next illustration. In this illustration, it is given a mechanism consists of a part which is translated with velocity u. This part, it is moving with velocity u, and rod AB, this rod AB of length L and mass capital M, hinge at A. It is hinge at A at this point, right? The rod rotate about axis A with angular velocity omega. That means motion of the rod is translational and rotational combined. Find the kinetic energy of the rod when it is vertical. We need to calculate the total kinetic energy of the rod in this orientation shown in the figure. Okay, so let us make the diagram to the next page. This is rod AB, and this end is moving, A end is moving with velocity u, and this is the center of mass, right? Let us assume center of mass is translating with velocity vcm, and we know this rod is a rigid body, then angular velocity of the rod about its center of mass will also be omega. That will be in the same sense as we are given in the question, in the clockwise sense, and here is also in the clockwise sense. So this is the diagram, and we know total kinetic energy is the summation of the translational kinetic energy plus rotational kinetic energy. Okay, we know translational kinetic energy is associated with the center of mass. That's why it is written as half m vcm square, and translational kinetic energy is associated with the rotation of the body about center of mass. So it is written as half ICM omega square. Okay, we know the velocity of end A, that is u, in the rightward direction. In vector notation, we can write velocity of point A is the velocity of A with respect to C plus velocity of C, or you can write velocity of A equal to velocity of C plus velocity of A with respect to C, like this. Okay, and we have assumed velocity of C, that is the velocity of the center of mass, is vcm. So this is vcm, right? And let us assume rightward direction is positive and leftward direction is negative. So we are not going to use I cap, j cap, etc., and we are writing directly positive or negative instead of writing the vector notation. Okay, so here we can write vc vector is equal to vcm with the positive sign, and you can observe here velocity of A with respect to C, its sense of rotation is the clockwise. That means the motion of point A with respect to C will be in the leftward direction, and this distance is L by 2. That means the speed of A with respect to C due to rotation of the rod should be equal to omega multiplied by L by 2 with a negative sign. So here in the vector equation we can write velocity of A, that is equal to u with a positive sign, that should be equal to vcm minus omega L by 2. From this equation you can observe we are given omega, we are given u, That's why we can calculate the value of VCM. VCM should be equal to U plus omega L by 2. So we got the velocity of center of mass in term of the given parameters, that is U and omega. Okay. Now we are in position to calculate the translational kinetic energy as well as rotational kinetic energy, because we know VCM and omega is given, and ICM is, this is a solid rod. So ICM about center of mass should be equal to ml square by 12. So total kinetic energy is equal to half m, capital M, U plus omega L by 2 whole square plus 1 by 2 ml square by 12 omega square, this one. Okay. Now we can expand this term. So we can write this term as 1 by 2 m U square plus omega square L square by 4 plus 2 multiplied by U multiplied by omega L by 2. So this is U omega L, and this is ml square by 24 omega square, right? We can further simplify. This is half m U square plus 1 by 8 m U square L square plus 1 by 24 m omega square L square plus 1 by 2 ml omega U, right? Now you can add these two terms. The summation of this 1 by 8 ml square m L square omega square plus 1 by 24 m omega square L square will be 1 by 6 m omega square L square. So final result is total kinetic energy is equal to 1 by 2 m U square plus 1 by 6 m L square omega square plus 1 by 2 m L omega U. Okay. Now let us move to next illustration. In this illustration, it is given a rod of mass m, length L is connected with a light rod of length L. You can observe here in this diagram, this is a light rod of length L, and this rod is having the mass m and length L. It is given the composite rod, this composite rod is made to rotate with the angular velocity omega. Okay, you can follow the diagram. We need to find number 1, translational kinetic energy, number 2, rotational kinetic energy, and third part we need to calculate the total kinetic energy of the rod. This will be of course summation of this and this part. So let us make the diagram to the next page, this one. The distance of the center of mass of this rod from rotation, center of rotation here from hinge point, you can say that is 3 by 2L. Okay. And let us assume the velocity of the center of mass is Vc, and it will be in the downward direction. This is Vc. Okay. And we know a rigid body have one very important property, that angular velocity remain constant about any point. And you can observe this rod is rotating, rod is a rigid body, and it is rotating about this hinge point with the angular velocity omega in the clockwise sense. That means we can write the angular velocity of the rod about center of mass of this rod is also omega in the clockwise sense. This is the angular velocity of the rod about center of mass, right? Now we can write translational kinetic energy, that is equal to half m Vc square. Vc is the velocity of center of mass, that should be equal to omega multiplied by radius of rotation about hinge point, that is equal to 3 by 2L. So we can write omega multiplied by 3 by 2L. Okay, this is the velocity of center of mass. Now we can substitute the value of Vc in this equation. So this equation will become half m multiplied by 3L divided by 2 multiplied by omega, right? So we can write this equation. Now we can simplify. This will be equal to 9 by 8 m omega square L square. This is the translational kinetic energy of the rod. Now we have solved first part. Now we can write rotational kinetic energy. Rotational kinetic energy should be equal to half Ic omega square. Ic is the moment of inertia about the center of mass. Okay, and you know the moment of inertia of the rod about center of mass is ml square by 12. So we can write 1 by 2 ml square by 12 multiplied by omega square. Okay, so here we can write 1 by 24 m omega square L square. Now we have solved second part, that is the B part. Now total kinetic energy is the summation of the A part and B part. So we can write total kinetic energy equal to K translational plus K rotational. Let us write K translational and K rotational value which we have calculated in the previous slide. Okay, so now we can add these two terms, total kinetic energy summation. Okay, now this will be equal to 27 divided by 24 m omega square L square, that can be further written as 7 by 6 m omega square L square. Okay, this is the total kinetic energy of the rod system. Let us solve the same problem, especially total kinetic energy of the rod, by second method. We know total kinetic energy of a rotating body about a fixed axis equal to rotational kinetic energy about that fixed axis. That means if we know the moment of inertia about an axis passing through this point, that is the hinge point, we can write kinetic energy, that is the total kinetic energy, as half Ip omega square. Okay, we can calculate Ip by using parallel axis theorem. So let us use parallel axis theorem. Parallel axis theorem is moment of inertia about the axis passing through this point, say P point, equal to Ic, that is the moment of inertia about the centroidal axis, plus m multiplied by the separation between the parallel axis square. That means Ip equal to Ic plus m multiplied by 3 by 2 L whole square. We know Ic is moment of inertia of the rod about the centroidal axis. It is having the value ml square, and this is equal to m multiplied by 9L square by 4, right? If we add, this value will be 7 by 3 ml square. Okay, now we can write the total kinetic energy. If we substitute the value of Ip from this equation, that will be equal to K total, that is 1 by 2 7 by 3 ml square multiplied by omega square. You can observe this value is same as we calculated in the previous method. Okay, now let us take one more illustration. In this illustration, it is given two beads each of mass small m are welded at ends of the two light rods, each of length small l. This is small l length, this is also small l length, and this is bead number 1 and this is bead number 2, and you can observe in this diagram this bead is moving, it is having speed v at this instant, and the system can rotate about this hinge and there is no friction anywhere, and we need to find the ratio of the translational and rotational kinetic energy of the system. Okay, so let us make the diagram to the next page. We know translational kinetic energy is associated with the center of mass of the system, and we write translational kinetic energy as half m multiplied by Vc square. This is the expression of the translational kinetic energy. M is the total mass of the system, Vc is the speed of the center of mass of the system. Similarly, we can write rotational kinetic energy as half Ic omega square. Ic is the moment of inertia about the centroidal axis. Okay, this is the center of mass of the system C. We know this distance, the distance of the center of mass from this bead is L by 2, and this is also L by 2. Okay, and if we want to find the distance of the center of mass from rotation axis, this should be equal to L plus L by 2, that is equal to 3 L by 2. Okay, this is denoted by RC. Right, we can write this term, that is equal to 3 L by 2, that is RC. And if we write the angular velocity of the rod, because angular velocity is not given, we are given the speed of this rod. This should be equal to, that is V should be equal to omega. Omega should be the angular velocity like this. So we can write omega multiplied by 2L equal to V. That means omega equal to V divided by 2L, we can write. Okay. So V is known to you, 2L is the total length, so we got the angular velocity. Velocity of the center of mass can be calculated by using the formula V equal to omega r, and omega is the angular velocity, and we know the distance of the center of mass from this point is 3 by 2L. So VCM equal to omega multiplied by 3 by 2L. Okay. Now we can substitute the value of omega, that is V divided by 2L. So VCM should be equal to 3 by 4 V. Now we can substitute the value of VCM in the formula, that is half m, m means total mass, multiplied by Vc square. So let us write the translational kinetic energy of the system. This is half, 2m is the mass, total mass of the system, and VCM equal to 3 by 4 V. So after calculation, this is equal to 9 by 16 mv square. Now let us find the rotational kinetic energy. Rotational kinetic energy can be calculated if we know moment of inertia of the system about the center of mass. We know rod is light and distance of the mass m from center of mass is L by 2, and this is also L by 2. That means the moment of inertia of system about the centroidal axis should be equal to m multiplied by L by 2 whole square plus m multiplied by L by 2 whole square. Right, and if we calculate, this value is equal to ml square by 2. So we got the value of IC. Now let us write the rotational kinetic energy as half ICM omega square. ICM equal to ml square by 2. So let us substitute this value, and we have calculated the value of omega in the previous page. This is V divided by 2L. That's why we have substituted here. So this value is 1 by 16 mv square. And in question, we need to find the ratio of the translational and rotational kinetic energy of the system. So the required ratio should be equal to translational. We have written translational kinetic energy as 9 by 16 mv square. That means 9 by 16 mv square divided by 1 by 16 mv square. That means this value should be equal to 9.